For all integers a, b, c, and d, if a divides c and b divides d, then ab divides cd. Let's prove this. Here's the definition of divides. We start by writing proof. We're going to assume a, b, c, and d are arbitrary integers, and assume that a divides c and b divides d. Now these are good assumptions because the arbitrariness of a, b, c, and d will allow us to prove that this statement is true when we use universal quantification for all integers. Since this is an if-then statement, we can assume the premises of the implication, and now our goal is to show that AB divides CD. Now, since A divides C and B divides D, then by definition of divides, C equals A times X for some integer X, and D equals B times Y for some integer Y. Now the goal is to show that AB divides CD. So at the bottom of this proof, we should say, therefore, AB divides CD. We can work backwards from our conclusion here to narrow the gap between where we are in the proof and the conclusion. Since the goal is to show that AB divides CD, then we should reference the definition of divides to further break down what it is that we need to show. By definition, that means the step before this needs to be that therefore CD equals AB times Z for some integer Z. That way we can come to our conclusion by definition of divide. So far we've backtracked from the conclusion just a little bit. We need to somehow get CD here. Now we have a C and we have a D, so to get CD, we could multiply these two equations together by multiplying the left-hand sides together and then separately multiplying the right-hand sides together. The results of those two would be equal to each other. So since C equals AX and D equals BY, then CD equals AX BY. Now that's really close to what we're trying to get here. We're trying to show that CD equals AB times some integer. And this almost looks like AB times some integer. So CD equals AX times BY, which is the same thing as AB times XY by the commutative property. So now we can see what our Z is going to have to be. Z is going to have to be X times Y. Since X and Y are integers, then XY is an integer, and that's by closure of multiplication. So XY equals Z for some integer Z. And now we've bridged the gap between our conclusion and our assumption. And that should finish our proof. Thanks everyone, and I'll see you in the next video.